All right, good morning. The second topic in Unit 5 in atomic structure is electron configurations. So if you remember back to when we did this in honors or regular chemistry, it's a matter of how we fill these atomic orbitals. So when we have the nucleus and we have the energy levels, the first ring is the first energy level and the second, what atomic orbitals exist on each of these rings and how do we fill them? The big thing here is the sequence problem. You just got to know and memorize the sequence at which it is needed to fill those atomic orbitals. All right? And there's a couple different methods that you can utilize to do so. Okay? The first is this thing called the diagonal trick. And you'll notice right here, I have labeled all of the s orbitals. And the s orbitals, there's an s orbital on every single energy level. 1s, 2s, 3s, 4s, all the way to 7s. You'll notice on the periodic table, when you look at the periodic table, that there are 7 periods which coincides with the energy levels. Okay? P orbitals. There are p orbitals all the way from 2 to 7. However, there's not a p orbital on the second floor. D orbitals, 3d to 7d. There's no d orbitals on the first and second floor. And F, there's none on the first, second, or third values. Now, because of that, what you have to just remember is that you have to remember the letters S, P, D, F, and you have to just remember that each new floor, we gain a new letter. And then the big key is to get this written down right how we can see it right here. Now, how does the diagonal trick work? We start with a diagonal line that crosses over the top upper left corner. So the first orbital that we fill is 1s. The next diagonal line cuts across, 2s. The next diagonal line, and this is 2p, 3s. The next diagonal line, 3p, 4s. 3d, 4p, 5s. 4d, 5p, 6s. Okay? And we could just keep going on all the way to fill the atomic orbitals. Okay? So that's called the diagonal trick, where we can use that to figure out the orbitals. You can see my first couple of lines were a little bit heavily skewed, a little bit too steep of an angle. We want to just shallow that angle up a little bit. Okay? But that is called the diagonal trick, a way to memorize the sequencing of orbital filling. There's another way that we can also get the same sequence, and that is just knowing the periodic table, as I've already drawn up here. There are 4 blocks in the periodic table that coincide with what orbital shape is currently being filled. Groups 1 and 2 is called the S block, 3 through 12 is the D block, 13 to 18 is the P block, and the group that's pulled out is the F block. So the periodic table also tells us the answer. Now remember, helium is placed over here, but configuration-wise, helium actually would belong here. So we would have, right here would be the 1s. Then we have 2s. Then we have 2p. Then we have 3s. Then we have 3p. Then we have 4s. And then what you have to just remember, this is the tough part with this, is that the D block is always one behind. So this is 3D. After the 3D comes the 4P, 5S, 4D, 5P, 6S, and then the F block is pulled out, which is 4F. Then we come back and fill the 5D. So the F block trails by 2, and the D block trails by 1. The S and P are in the same level. And we just keep going on and on from there. Okay? So that's another way we can get to the order which we fill orbitals. Along with that, you just have to know the max capacity. You have to remember that an S will take up to 2 electrons to be completely filled. P's, they come in groups of 3. Each orbital takes 2 electrons, spin up, spin down. That takes up to 6. D is 10, and F is 14. Okay? You can also get that by looking at the width of the columns. The S block is 2 wide. The D block is 10 wide. The P block is 6 wide. The width of the block can also tell you that answer too. All right, so let's go ahead and do some practice here. First thing to be able to do electron configuration is to be able to figure out how many electrons each of these elements have. So we look at the element chlorine. Chlorine has got 17 electrons. Right? First orbital we fill is 1s, and s takes up to 2 electrons. Then we fill 2s, 2 electrons. 2p, p takes up to 6. That gets me up to 10 electrons. Then 3s, another 2, and 3p with 5. The superscripts should add up to 17, and that is the electron configuration of the chlorine atom. Whenever you see the word atom, again, that means that the number of electrons equals the number of protons, and therefore the number of electrons should equal the atomic number on the periodic table. Okay, go ahead, pause lecture now, and go ahead and do iron and do tellurium. All right, iron's got 26 electrons, and you can see there that it ends at 4s2, 3d6, and tellurium with 52. We got to get all the way out to 5s2, 4d10, and 5p4. Okay, one note with valence electrons. The valence electrons are the electrons found on the highest energy level. So if you look at chlorine, the 3s and 3p, because they both begin with 3, this is the highest energy level. This would tell me that chlorine has got 7 valence electrons, which it does. It's in group 17. Iron, the 4s2 are the only valence electrons because the 3d orbital is part of the third floor. The fourth energy level is 4s. This has got 2 electrons, so iron's got 2 electrons. In tellurium, 5s and 5p, again, the highest coefficient gives me the valence electrons. That gets me 6 electrons. Tellurium is in family 16, 6 valence electrons. So that's how we can get the valence electrons from the electron configuration. Again, how many electrons fill an orbital? 2 electrons fill an orbital. Every atomic orbital. The only thing different about 2 electrons in the same orbital is they spin in different directions. How many electrons fill the 3D sublevel? Well, the 3D sublevel comes in quintuplets, 2 in each, so it takes a total of 10 electrons. And as I said, what's the only difference between 2 electrons in the same orbital? And that is the fact that they have to spin in opposite directions. Some things that we've talked about. Now, orbital diagrams are looking at being able to do those arrow methods within the configurations. Okay, and to do that, we have to apply the 3 rules, if you remember. Hund's rule says if we have equal energy orbitals, like the 3D or the 3p, p's come in 3s, that we put 1 electron in each before we can start doubling up. Okay. Aufbau says we fill the lowest energy orbital before we can fill the next one. We fill 1s before 2s. When 2s is full, then we fill 2p. We fill the lowest energy orbital, and then we go to the next one. And Pauli exclusion principle says that if we have 2 electrons in the same orbital, they must spin in opposite directions. Okay? Paired electrons are where we have 2 electrons in the same orbital. Unpaired electrons, just vocabulary, means there's only 1 electron in that orbital. All right, let's turn the page. So here is an energy orbital diagram, and now you can see we fill 1s first, then 2s, because we fill, Aufbau says we fill the lowest energy orbital, so the orbital lowest in energy, okay? Then 2p, then 3s, then 3p, and this is where you can see why we fill 4s before 3d. You can see 4s is a little bit lower in energy than 3d, and that's why we fill 4s before 3d. Okay? So right now, pause the lecture now, use this energy diagram to be able to do the orbital diagram for carbon and iron. All right, carbon with 6 electrons is 1s2, arrow up and down, 2s2, arrow up and down, 2p. Hund's rule says we can't put the 2 electrons in the same p orbital. We put 1 in each, and this, the reason we do this is we want to minimize the electron repulsion. So, because 2 electrons repel each other, and again, spinning in opposite directions helps that, but it's still 2 electrons in a very same tight space. So if we're able to put electrons in equal energy orbitals, 1 in each, that is going to be a much more preferred orbital diagram. Iron, we fill the 1s, 2s, 2p, 3s, 3p, 4s. When we get to the 3d, again, Hund's rule says we put 1 in each, so we put 5 electrons into 3d, and we have 1 left. And so there's 1 orbital that is doubled up, and then we have the other 4 have single or unpaired electrons. Okay? Lastly, let's do electron configurations of ions. And lately on the national exam, they've done a lot more of this, to do the electron configuration of ions versus atoms. Now with ions, you have to remember that the number of electrons now will not match the atomic number because electrons have either been added or removed to create the ion charge. So nitrogen, N, has an atomic number of 7. So when it's an atom, it has 7 electrons. But being a -3 ion, it has gained 3 more, which means now it's got 10 electrons. So again, negative, we add. Positive, we subtract. So for nitride, the nitride ion, it'd be 1s2, 2s2, 2p6. And right there would be the electron configuration of the nitride ion. The nitrogen atom would be 1s2, 2s2, and 2p3. So you can see there it has the 7 electrons like it normally does. But again, to fill the second floor, it needs to gain 3 more, and this is why nitrogen forms the -3 nitride ion. All right, go ahead, pause the lecture, and now do the other 4, please. All right, magnesium has got 10 electrons because magnesium normally has 12, but being +2, it's lost 2, so it's got 10 electrons left, and it has the same electron configuration as the nitride ion. Okay? And that's because ions try to achieve the electron configuration of a noble gas because that is the most stable electron configuration. So magnesium losing 2 electrons is the same number of electrons as the nitride ion. So the magnesium ion and the nitride ion has the same number of electrons. However, they do have different sizes. Even though they have the same number of electrons, they do have different ion sizes, and that has to do again with Coulombic attraction, which we'll talk more about on Monday. But magnesium has got 12 protons in the nucleus, nitrogen's got 7 protons in the nucleus. Even though they have the same number of electrons and they're in the same atomic orbitals, which ion is going to be smaller? Hopefully, you said magnesium. 12 protons are going to pull on 10 electrons more than 7 protons will. So magnesium ion has got a greater Coulombic attraction, making it much smaller than the nitride ion. So ions, or ionic sizes, just like atoms, we have to look at the nuclear charge, and the one with the higher nuclear charge will create a smaller radius. Okay? When we get ions in the D block, I want to pause the lecture and show you what happens. So this is the electron configuration for the manganese atom, which has got 25 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. If you count, this has got 25 electrons. Now, for manganese to be +2, it has had to lose 2 electrons. Which 2 electrons are lost first? And most students right away would look at the 3d orbital and pull off 2 electrons and make 3d3. However, that is not the case. What ends up happening is the electrons that are pulled off are the 4s electrons. Why? They are in the highest energy level and are considered the valence electrons, even though they are a little less energetic. So when the manganese ion forms, when any ion forms in elements in the D block, you are always going to pull off the highest coefficient electrons first, which usually is the s electrons. So the manganese ion would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, not 4s2, 3d3. Make sure I really recommend with the D block that you write out the atom configuration and then think about it logically and think about which electrons come off first. First we pull off the 4s, and then if there's more electrons to pull from, then we start pulling from the 3d. Go ahead and try that and do iron 2 and iron 3 and see what you get. All right, iron as an atom has got 26 electrons, and it has a configuration at the very end of 4s2, 3d6. So when an ion of it forms, the +2 ion, which we know iron forms a +2 charge, the first 2 electrons that are pulled off is the 4s, leaving 3p6, 3d6. Then iron can also form a different oxidation state with removing one more electron, and now we'll pull from the 3D, creating 3p6, 3d5. Now, why do d block elements sometimes form multiple oxidation states? And that's because they can pull from both the s and the d orbital. And if you look at iron up here in its orbital diagram, you'll notice a very important thing, and that is only one of its orbitals is doubly occupied. This is why iron 3 is such a preferred ion state of iron, because not only can we remove the 4s electrons, but we can remove one more electron from the 3d, and now all of the electrons in the 3d are singly occupied. That removing of that electron minimizes the repulsion in that 1d orbital, and that is a very stable configuration. So this is why ion elements in the d block can form more than one oxidation state. All right, so as long as you remember the sequence and you do a bunch of practice, this is something on the test that you should be able to do fairly easily. The big key is make sure you can do configurations of ions and know which orbitals you pull from first, and then when you pull from second, and so on and so forth. Okay? Again, thanks for listening.